Hello, this is Kerry Schutz with MathWorks, and we're back with part 4 of our using frames in Simulink and how they can be tricky and how they can be useful, a video series. So in this part 4, we're going to focus on benchmarking an 8th order elliptic low-pass filter. So something a little bit more than what we've looked at in the previous videos on this topic of frames in Simulink. So we're going to cover really, how you do benchmarking, some of the subtle details of it along the way. So I hope that's also helpful. And then we'll look at many variations of how one could implement this elliptic filter and what impact those different implementations have on speed. So let's jump over to the tools. I'll jump into my model, my test case model. Let's see, where do I have it down here? One of these. Here we go. I'll pull this over into my main screen that I'm sharing. And what you're going to see on the, if you're looking up and down the model, is that I have some type of biquad filter in the middle. Got, looks like 6 different implementations of it. And each one is going to be just a little bit different. I've got a similar scope on the right-hand side. I've got very similarly configured sine wave driving it. In fact, it's always the same frequency, always the same sample rate. It's really just the frames that vary from one implementation or one block to the next. Well, okay, let's focus on one implementation at a time. So we'll start with the simplest possible use case, which is where I started earlier. And that was with a sample-based implementation, a sine wave block. Here, 1 sample per frame, 48 kilohertz sample rate, 1 kilohertz sine wave, unit amplitude. Okay, and then we've got this biquad filter and a scope. Now, you can see that everything else here is commented out. And in fact, I've even commented out the scope here, but I'll uncomment it for starters. So let's just uncomment it. So let's just run. And I'm running here for lots of samples. You can see that I'm running for 5 million samples at this 48 kilohertz sample rate. So I'll call my scope up. We'll drag it onto my main screen. I'll hit play. And you can see, well, it's running right along. You can't tell exactly how many cycles are in there. But, we can see it nonetheless. We zoom in, we'll start to see the individual cycles of this 1 kilohertz sine. We even see that little transient start up there at the beginning, the transient response of the filter. So in this video, we are assuming that we've done all the verification on this filter, that we're getting the right answers in each and every filter variant. So I don't want to concentrate on how do we verify a filter. In this case, I want to concentrate on performance impact of using samples versus using frames in a simulation, in a Simulink simulation. So here we're assuming we've got a good response, it's valid, and now we want to measure time. Well, I just so happen to put in if I right click in the white space in the model, select model properties, select callbacks. On my start function callback, I've got a tick. On my stop function callback, I have t-run equal talk. So that does a tick and a talk from the time I hit play to the time the model stops over that 5 million sample span. And it said it took, in that case, it prints out in the diagnostic window, it says it took about 11.9 seconds to run that model. And that was, of course, with visualization on. If I were to disable the visualization and run again, you should get much faster times. Now, you have to be careful about doing that because Simulink can, in fact, optimize away the whole simulation if it senses that the results are not being used. So you have to pay attention to that. So that's why I have the logging on the output. Sometimes when it's not logging, it'll just say, well, you're not viewing the signal, you're not computing with the signal, you're not logging the signal. Therefore, I don't need to compute that output. And so you have to just be very careful that you're not fooling yourself when benchmarking. I'm going to run again. And it's going to run faster because the visualization is not updating. How much faster? Well, we're going to see here. And it tells us it took about 8.8 seconds here. So, and again, your mileage will vary, depends on other processes run on your computer. if you run this model, for instance, 3 times and get 3 different results, or 10 times and get 10 different results, the best, really most accurate way to benchmark it would be to take the fastest time. In this case, it looks like it took 7.9 seconds, and sometimes your subsequent runs are faster than your initial run. Initial run may be, in fact, the slowest if it's caching things up. So 7.9 seconds. I'm just going to leave it here at 8 seconds. I've said I ran for 5 named samples in normal mode, not accelerator, and it took 8 seconds approximately to run that, again, without visualization. If you wanted with visualization, you'd have to have another category in here that says visualizations were included. All right, what if we ran it in accelerator mode? That says we're going to compile the model, or at least pre-compile the model, some to C code, and compile it to some type of object code, and then run it. What kind of impact would that have? We can run that again. We would expect it, at least hopefully, to be faster. And indeed it is. It looks like it took about 4.9 seconds in that case. So I'm going to leave that previous spec I had there up. And again, this was using a filter that was designed using the Filter Designer app. So if I go over to my filters, I'll drag it onto my main screen. I designed this filter by just saying, okay, I want a low pass filter. Again, this is the Filter Designer app. You can bring it up by just, I should have mentioned here, you can just go to MATLAB and type Filter Designer. You can probably just type filter and then tab complete, and it would be this one right here. Once you do that, hit enter, it's going to create, well, a new instance of Filter Designer. In that case, I don't need a second instance, so I'll just keep my first one. And what I did was I said, okay, low pass filter, I want an elliptic IIR filter, I want to filter with feedback, essentially. That's the more tricky use case with frames. I'm going to design it to achieve a certain spec, which would be it's 48 kilohertz sample rate. The pass band goes out to 9600 hertz. The stop band starts at 12 kilohertz with a attenuation, minimum attenuation of 80 dB and 1 dB of ripple in the pass band. So that's the magnitude response you see up here in blue, and then it has this resulting phase response you see here in red with the phase and radians on the right-hand x-axis. And it says this filter is 8th order. It has 4 biquad sections, and that's really all you need to know at this point. It's double precision implementation by default. I'm not doing a fixed point one. And then if you want to build a Simulink block out of this, you want to take it to the next level beyond analysis and do implementation, you can go over here and say, I want to build up this model using either a sample-based or a frame-based implementation. I click on Realize Model here. I can do that again. I can call it filter, whatever. Today's date is what, 9/8/22. I can just say that, Realize Model, and it builds this filter 9/8/2022. I could swap that in place with this one, and it would be the same thing. And then if you double click on this block, you'll see the coefficients for the second order system matrix that were used, the scalar values for each stage that were used, the initial conditions, and so on. And then again, it's an input processing sample-based implementation. You can look at the response here on this dialog as well. Okay, so that's how I generated the block. But that's just one way to implement that from Filter Designer. There's many other variants, and that's why I have all of these different variations below. So that was the sample-based implementation. What about the next one? So let's comment out this one. So we're only focusing on benchmarking one implementation at a time. Now I'm going to enable this one with AlphaScope. I don't care about benchmarking visualizations at this time. Just concentrating as much as I can, isolating the effect of the filter changes. Now I've got a sine wave, still sample-based output here, but I'm buffering up 100 samples on my buffer block. And then I'm presenting that to my biquad filter, which now is a frame-based monolithic implementation. And by monolithic, I mean this is using a canned block from the DSP system library. So if I were to open up the DSP system library, this is the Simulink library browser, go down to DSP system toolbox, filtering, filter implementations, select your biquad, you could drag that into your model, or just use the filter designer and it will pull in that block, invoke that block, and fill out all the fields for you. which is what I did. Okay, so now what I did was essentially I said, hey, generate this in frame-based mode, realize model, don't build model using basic elements, that's to come. We're going to use a canned block, library block instead. And that's this block. And if you double click on this, you'll see that it's set to frame-based here. So the only real change there was they just changed the setting. We're going to run this again for the same stop time and see what happens in accelerator mode. And it is in frame-based mode, and it is indeed faster. So one of the benefits of running in frame-based mode should be, or is hopefully, acceleration of your simulation. Again, we're amortizing that overhead over a frame as opposed to each sample. We got about 4.2 seconds on that run, or 4.3. We could, again, run this a number of times when you're doing benchmarking. Typically, you want to do it a number of times there. I got about 4 seconds. I'm going to leave it right there at 3.9 or 4. We want to be really accurate about it. Let's just say 4. And so that's another number. Okay, let's take another one. What if we wanted a frame-based implementation, but instead of buffering up the output of a sample-based sine wave output, we just put the frame-based or vector operation on the source block itself. So in this case, the samples per frame is 100 here on the sine wave block. Instead of a scalar here going to a vector, we're going to go to a native vector here. I'm going to hit Control D to update the diagram. We'll see that it outputs a native vector. I'll comment this out, so we focus just on the third variant of this, and I need to also, I don't want that scope corrupting the measurement. And again, I'm logging the output. In case you're wondering how to log the output, you just right-click on the signal and just select that Wi-Fi log selected signals, and that would log in the input and the output. Okay, let's go ahead and run this. See what happens. Previously, I'd gotten, let's see, that ran super fast. It says here it ran in 0.76 seconds approximately. So let's run this. It ran so fast that it was almost like just scorching, like 5 million samples is not even enough to benchmark it. So I'll go up to 5E6, I'll go up to 10E7, which is what I was using before. Let's do that. So I get some time in the neighborhood of 4 or 5 seconds. That's a better benchmarking measure. If the time is too short, you're not really getting an accurate benchmarking time. So you want something, 5 to 10 seconds, let's say, in general. Here we got about 4 seconds. I'm going to stick with that. 10E7 samples took about 4 seconds. That is what we would call fast. So again, I'm just trying to, at this point, illustrate all the different ways your simulation speed can be impacted. So in this case, the only change I made was going from using a buffer block to putting the vector operation on the sine wave block natively. So big difference there in that case. Not necessarily expected. All right, so let's go ahead and comment that out. And just spoiler alert, it's going to be hard to beat that number. That's pretty fast. Now, here's the snag though. The snag is I've been using a canned filter block, this biquad filter block. And you don't have any control over how that filter was implemented. It is a biquad, and that's it. You can't go in and tweak the architecture in any way, shape, or form. You can't remove a multiplier, add a multiplier, whatever. You just can't tweak it. And so many times people want custom filter implementations. So in this case, what I did to emulate that was I said, I'm going to use Filter Designer. Here, let's call that up. But in this case, I am going to say, I'm going to check this box, build bottom using basic elements. And I'll do the first one sample-based. And in fact, in this case, that's the only option we have. We can't get the frame-based option. So we did that, and that's what this implementation is here. Get rid of all these. So we're on the fourth one now. And you can see what it looks like. We've got the input port. We've got our scalars for each stage. We've got our biquad structure with our 2 delays and 3 multipliers. And then we go to the next stage with our scalar, multiplier, and another biquad, and so on and so forth. And each delay is set up, in this case, to be sample-based. This is our sample-based version. And there's one more stage unto the output. Okay, and now we want to benchmark it over that same, I'm going to go back to my original stop time, which was 5e6. And let's run again. And that still runs pretty fast. It's taking, let's see, view diagnostics, took about 4.7 seconds. So I can, actually, that ran a little faster than I had it before, so I'll just update that time there to be about 4.7 seconds. And, okay, so that's good. I mean, that's a reference point. What if we now tweak that filter? And again, the purpose of comparing the filter monolithic or shipping block to the primitive space, that's what the P stands for, is monolithic versus primitive space. The purpose of this is to have something which is customizable. You can change anything here. You can go in and add or remove this to any custom filter implementation you want. And many times that's required in real life. All right, so I'm going to comment that implementation out. And now we're going to do the same thing. We're going to have this custom primitive-based elliptic low-pass filter implementation, except that it's going to be frame-based. So if I go in and look now at the delay blocks are set up for frame-based processing. Likewise, the scope on the output, were I to, let me just uncomment it. Remember from our previous videos, if you're using frame-based processing, scope 5 here, then you want to have your input processing and your scope also set to frame-based. So again, we're not logging, or we're not viewing, I should say in this case, we're only logging the data to the base workspace. So comment out the scope so it doesn't alter the benchmarking measurement consistency. And our sine wave block is set up to output a frame of, again, size of 100, same frequency, same sample rate. So let's run that. Now I've got some little hint here. If you read that, it says extremely slow. Well, let's just see what that translates to. And slow, if you look down here at the progress bar, well, it hasn't even inched over yet. We haven't even got to 1% done of the simulation. In this case, we're going up to about 104 seconds, and we're not even only up to 1/10 of a second yet. So this is just geologically slow at this point. So I wrote extremely, but really geologically would probably be a better term here. So I'm going to hit stop. And the reason for that is you notice all these warnings I'm getting. We saw this in the previous videos. I've got a bunch of algebraic loops. In fact, I've probably got 4 of them because I've got 4 stages of this biquad filter. And that is really having a huge, for the worse or deleterious effect on simulation speed. All right, you can see there I ran for 30 seconds and I didn't even get up to, 1% of my simulation time. So that's really bad. And again, so we can work around that. As we did in the previous video, we used that For-Iterator implementation of the filter to work around the slowness. And so if we go here, I'll uncomment this. And again, we're focusing just on, now if I double click, go underneath the hood here, we'll see that I've got the For-Iterator block, which is counting up 1 through 100. It's pulling off the elements of this vector one at a time into our filter, and again, we got a frame-based version of the delay block, and then on the output side, we've got the assignment block again being driven by the same 1 to 100 count from the For-Iterator. That's just a go-to from tag, and we're initializing the output to zeros. Okay, so that's the same structure we showed and concentrated on in the previous part 3 video. So let's run that and see what kind of time we get. And again, it's just done. So that's where it's like the previous, the fast implementation. I believe that was what, the 4th one? Let's just see. The one that was extremely fast was this one. It was actually, I guess, the 3rd one. So now we're on the 6th one. The 3rd and the 6th ones are the very fast ones. So if I were to go up to, 10e7, let's say again, like we had before, run this again, and it's just going to be in the neighborhood of 4 seconds again. It's about 4.6 seconds. So again, very, very fast. All right. So I hope that's helpful. It kind of lets you know that when you're using Simulink, almost everything matters when it comes to simulation speed, or everything can matter, and you have to be aware of that. Or it's the more you're aware of these impacts of these so-called subtle setting changes and they can have on simulation performance, the better off you'll be. Many people say, something like, well, Simulink is slow or Simulink is fast. And the truth is, it's all of those things. Just like if you were programming in any language, depending on how well you use it, where you are of all the features, you can speed it up or slow it down by, multiple orders. So the Simulink here is no exception as a simulation environment. All right, I hope that was helpful. Thanks for tuning in on this video series on using frames in Simulink. Signing off now.